Right. Good evening, everyone. Hope you can hear me.
Evening po, sir.
Thank you. Our agenda this evening is to our agenda for this evening is to have a tutorial on the exercise on simple linear regression.
Tuwing gabi, ay,
Right. This is the probably one of the most commonly used analysis in geology. Right. Probably 90% of the equations which you will encounter in your geology career probably are mostly based on just a simple linear regression. And I think it would be advantageous for you if you're familiar with how should you be utilizing regression equations, or even how you can do a simple linear regression for your studies or for your future work. And let's start with some definitions. A regression analysis will tell you how two or more variables are related. And let's revisit the old faithful geyser back in the covariance lecture. Let's say you wanted to forecast the eruption, the waiting time for the next eruption based on the duration of the eruption, right? As mentioned earlier, right? The longer the eruption or the longer the explosion, you're probably draining the fluids inside the geyser chamber, right? And logically, you would think that if you erupted a lot of stuff out of the geyser, it would probably take a longer time for the geyser to refill itself and eventually build up enough sufficient pressure to cause another eruption, right? And before that, let us define our conventions. The response or dependent variable, we call it the y, right? It's the variable we're interested in. It's a variable which we want to predict or forecast. And then the other one is the predictor or the independent variable, usually denoted y. And it's also called the explanatory variable. And this one is supposedly this variable supposedly this is what we use as an input, right, when we're trying to make a forecast on the value of variable y. Normally we would set the x variable or the independent variable whenever the variable is readily available to when it's relatively easier to measure or collect, like for example rainfall data, or let's say dimensions of a fossil, right? And usually the response variable would be a value which could be a little bit more challenging to obtain, like for example the volume of a fossil, or the mass of a fossil, or the likelihood of flooding, right? And since in this session we will be only dealing with simple linear regression, we will only have just one predictor variable, just one input variable. And this is what we call a simple linear regression model. You just have one predictor or one independent variable in use, right? Right, and you're just gonna see here, this is the data for the Old Faithful geyser, right? Duration of the eruption, and then the waiting time for the next eruption. And by convention, the X values would, or the predictor variables, or the independent variables would be placed in the X-axis, and then the response or the dependent variable would be placed on the Y-axis, right? And the simple linear regression will take this form of a line equation. You have your y is equal to mx plus b. I'm sure you're familiar with that, right? M is your slope, x is your x value, b is your y-intercept. Okay. Later, we will show you a slightly different form of this equation, right? And and how we interpret the slope, it's really straightforward. If the slope is positive, or if m is a positive value, it implies that there's a positive linear relationship. Or if the x value is increasing, it also means that the y value is also increasing. If the slope is negative, it simply means that as you increase your y, your x will be decreasing, right? You can see this as a sort of a a form of human relationships. Okay, so this is a good kind of a relationship. You do the same. You're always in agreement of what you want to do. This one is a sort of a form of a toxic relationship. If the other party wants to do something, the other one will try to do the opposite way. Then the third one, this is probably the worst. If the slope is zero, whatever happens to x, the other variable remains constant, meaning there's no reaction, right? Whatever you do, there's no reaction, there's no response from the other party to the relationship, right? We also have to take note that the regression line will rarely fall exactly on the straight line. There will always be some scatter, there will always be some error. And let's have a quick example. We have, let's say, a hydrologist created a model to predict the volume of a flow on a river, right? River flow is simply the velocity of the river flow multiplied by the cross-sectional area. Right? And of course, river flow or river discharge is actually challenging to measure. You need to have some proper instrumentation on the river. You need to find a way to measure the velocity of the river flow, and you also have to establish the area of cross-sectional area of the river, right? If you're gonna do this as a one-off task, it's doable. But if you're gonna do this every day, it can be quite tedious, right? That's why the hydrologist tried to link or predict the volume of the river flow based on the daily rainfall data. Rainfall data is a lot easier to measure. Right? You just need some uh have a rain gauge. It could be an automated one, could be a manual. It doesn't matter. It's relatively easy to obtain. Anyway, the predictor equation is set up as follows: y, or the volume of flow, is equal to 1.6 plus 29x, right? And this is in units of gallons per minute. And we can simply interpret this as follows. The y-intercept is 1.6, and this simply means that on a day with no rainfall, like if we set the x to 0, we can expect a baseline river flow of 1.6 gallons of water per minute flowing into the river. On the other hand, if it rained like 1 inch on that day, you can expect the flow in the stream to increase by an additional 29 gallons per minute, right? So it would be something like 30.6 gallons per minute of water flow. And then if it rained 2 inches on that day, like if you plug in the value of 2 in your X, you will get something like 58 gallons plus 1.6. So that would be 59.6 gallons per minute of our river flow rate. And of course, as we have done in the other lessons, we can get a lot of information by simply doing a scatter plot of our data, right? We can gain a lot of insight by doing a simple scatter plot. And in here, again, we're back again with the old faithful geyser. And from here, you just have to keep in mind what patterns do we see, like what is the direction of the relationship, right? And here, at least you can see here, as the eruption duration is increasing, the time weighted is also increasing. Therefore, it's a positive relationship. Both are increasing. I mean, both are going in the same direction. What is the relationship? Is it linear or non-linear? Again, you can see here, maybe except for this outlier, most of the points are showing a more or less straight line pattern. Therefore, we can say it's a linear relationship. In terms of the strength of the relationship, we can see that like most of the area of the chart is a more or less a continuous the values more or less line up together, right? So if you can see that if only half of the values are lining up together, like the plot is something like this, you can see that maybe it's a weak relationship. But in here, you more or less have most of the data points. They're quite lining up. Okay, they're more or less complete. Okay, and you can probably see that it's a strong relationship. And then the last question is whether there are outliers or extreme values. The definition of outliers or extreme values is that the removal or addition of this value will significantly affect the regression or the straight line trend of the data, right? You can see here, I mean, if you just let's just try to draw a straight line for the majority of the data points, you can quickly see that this point is quite isolated, right? And this is probably an outlier for this data set. And we have more examples here. This one is a height versus weight relationship, right? Like we're trying to predict the weight based on the height of the student. Of course, this is subject to pitfalls. Of course, you can have a student who is tall but would be is skinny. You also have a student who is tall but is quite overweight, like me. So you will definitely see a scatter in the data. But otherwise, let's see the relationships. Again, we're seeing more or less you're seeing a positive, right? If the height is increasing, generally the weight is also increasing. Now, in terms of the shape of the relationship, be honest, it's really not straightforward. It could be linear, but you just have so much scatter in your data. Like it could be something like an exponential. Okay, be an exponential trend, could be anything. Relationship weak, moderate, or strong. Again, you have the data points are more or less complete, right? Like they just line up together, but you have quite significant number of outliers. So probably this is just a moderate strength of relationship. And then you have a lot of outliers. Depending on, of course, the definition of outliers will depend on the shape of relationship that you're trying to draw. If you're trying to draw a straight line, these points might be the outliers. On the other hand, if you're trying to draw an exponential line, the outliers might be simply limited to this one, right? And so on and so forth, right? And you have another example here. You have they're trying to relate the first test score of a student relative to the second test score, right? And of course, you're expecting students to have an increasing test scores, right? If you're just going to repeat the same exam, the trend should be positive, right? If you take the exam again, the the score should be increasing, right? So, however, you can see this pattern, right? It could be positive, right? You can just trace this trend like this one. It could be something close to zero if you're gonna ignore these outliers, right? Meaning there's no relationship between the first test and the second test. And you can also see here that there's a big gap in the data points, right? In the first half of the data. Therefore, this is probably a weak relationship. And then again, outliers would be subjective, right? If you're trying to define a positive linear relationship, then probably the outliers would be this one, and even this one. However, if you're trying to define a flat relationship, probably this ones would be the outliers, right? Okay. Right, let's have a review of the correlation coefficient. This is one of the parameters that we'll be calculating while doing a linear regression. Right, let's define it's a measure of the strength of linear relationship between two variables, and it's usually denoted as a small r. or a Pearson's R. And this is the formula for calculating correlation coefficient. This is essentially the same equation which we encountered in the first lecture in week 1. Not gonna expound this one. And the properties of correlation coefficient, again, the values will take place anywhere between -1 to +1. The sign of correlation will tell you the direction of the relationship, right? If it's positive, then they're going in the same direction. If it's negative, they are going in the opposite direction. But either way, a negative or positive relationship is still a relationship. However, if the correlation is 0, it simply means that there's no linear relationship between the two variables. And this is a dimensionless number. And as the value approaches positive or -1, it indicates a generally strong linear relationship. Conversely, if it's approaching 0, you have a weak relationship. And this one, we're gonna talk about this one later. And the last one is that flipping the predictor and response variables won't change the value of R. I think this is one of the questions in the first lecture. Like, what would be the effect if we flip the x and y values and we tried it, and the result is essentially we get the same correlation coefficient, right? And these are examples of different values of correlation coefficient. You can see here the two variables are increasing, right, and in the same direction. Therefore, the correlation is positive. In here, as the x value is increasing, the y value is actually decreasing. Therefore, the correlation is negative. On the other hand, in this one, you have more or less a flat trend. Therefore, the correlation is probably close to 0. And the fourth one is probably the most important example here. As you can see, you can actually see a trend in this data, right? You have a sort of a parabolic curve or a parabolic trend. Okay. So again, not really familiar. I can't really remember the equations describing these ones, but this is sort of a circular or maybe sinusoidal equation, right? And this can be described mathematically, right? But for for our lesson, we only care about the linear trends or linear relationships. And in the perspective of linear relationships, this one is actually showing a 0 correlation, right? Because as you increase your x, right, your y is partly increasing, and then after a certain period, certain right, half of the values are actually increasing, and the other half are actually decreasing. And since correlation coefficient will only care about the average values, these trends are simply canceling each other out, and the overall trend is that you just have a 0, or yeah, basically a 0 correlation or a 0 linear relationship. However, again, there is actually a relationship. It's not just linear. Okay, so that's one caveat or disclaimer when you're doing linear relationships. Okay. In practice, we actually use transformations, right, for data sets which do not exhibit a linear trend. Okay, and I think that's one of the problems in the exercise. Okay, so you're gonna encounter nonlinear trends, and there are actually workarounds to sort of convert or transform a data, right? You can just transform the shape of a data such that you can still capture their you can still transform them into an approximate linear pattern. Okay, and from there you can do your linear regression analysis. Right, in regression, the model is just a linear fit of your XY data. Again, we're just drawing linear or straight lines, and the method used in obtaining or extracting that straight line is the least sum of squares method. Right, sum of squares is simply it's simply a measure of the distance, right, of the points from the trend line. Okay, right, and what we do is we simply calculate the sum of squares, right, of the data relative to the mean value. Okay, and from there we can derive the regression line, which should minimize the sum of squares. Okay, so again, I'm not gonna expound that one. Right, and the standard form for linear regression model equation. You have again your x, and then you have your slope. This time this is denoted by letter B, and then you have your x value plus your y-intercept, now denoted by A. And then finally you have your error term, right? And this is probably one of the most important stuff that that I think we should learn to utilize when we are using regression models or regression equations. I'll show that later, right? And these are just a few more equations. B, or the slope, again, is just equal to your correlation coefficient multiplied by the standard deviation of the y variable and then divided by the standard deviation of the x variable. Again, standard dev or standard deviation, this represents the scatter within your data set, right? So the bigger the scatter in your y variable, you will generally get a smaller slope. And then the bigger the scatter in your standard dev of your y values, this will give you a bigger slope of the regression. On the other hand, for the A, or the y-intercept, it's simply equal to your mean of your y values minus your mean of your x values multiplied by the slope. Right now, let's talk about the coefficient of determination, or this is also commonly called the R squared. So I'm sure you already saw this value in your stat, or even in your basic scatter plot in Excel. Coefficient of determination, or R squared will uh, simply tells us how much percent of change in the response variable y is accounted for by the predictor variable x, right? I mean, in simple terms, um if you initially had 8,000 pesos in your wallet, and then the following morning it's just uh zero, right? So if you know that you ate a meal at a restaurant and it cost you like 100 pesos, and then another 100 for maybe um for other expenses, right? Um you can see here that your loss of money is easily explained by your restaurant meal, right? However, if you know that you only spent so little, right? The day before, like you remember only spending like 200 pesos, right? But you only have now zero money, and this simply means that there's an unknown variable which caused you to lose money. So you might have dropped your change, or someone stole your money whatsoever. And that's the idea behind the coefficient of determination. You're just trying to explain what is happening in the x variable, and you're seeing how much is actually being explained by the predictor variable, right? And if we go back to the old faithful geyser example, sorry, no H. The correlation coefficient is 0.901, right? However, if you're calculating the coefficient of determination, you have to square your correlation coefficient. So zero point 0.9 squared, it will get you something like 0.81, or about 81%, right? This simply means that 81% of the response variable, or the 81% of the changes or the variation in the duration of eruption, is actually properly explained by the predictor variable or the waiting time, right? And this simply means that this waiting time variable is actually quite powerful, right? So it's single-handedly accounting for 81% of the date of the value that you're trying to predict, like for example, the duration of the eruption. Okay. Therefore, you still have like 100 minus 81, you still have like 19% variability, which remains unaccounted for, and this can be explained either by another unknown variable, like you can just add another variable in your regression equation, and hopefully can achieve like a 99% R squared. Maybe you can do that, or maybe it's simply explained by the errors in the measurements, right? On the other hand, if you're getting a very low or a relatively low coefficient of determination, like let's say zero point 0.1, it may probably tell you that you should be exploring other predictor variables, okay? Or you should consider other variables which may better explain or may better account for the behavior of your y variable. Okay. And of course, the interpretation of your R squared value is very context specific. Why? Because it hinges on how you did your regression analysis, which in turn will depend on which variables did you select. So this is very crucial in your regression analysis. If you're using the if you're not using the best variables, or which don't really relate well with your response variables, okay, you're probably getting a relatively weak regression, okay. And of course, the quality of data will also weigh in. on the value of your R squared. Okay, right? Now there's really no set value for what's an acceptable R squared value. Although personally, and I practice applied geology, right? Most of the equations which I see, or regression equations which I see, rarely go for R squared that's less than 0.7. Okay. So they usually aim for R squared that's greater than 0.7, meaning they always tend to look for variables or sets of variables which can explain for at least 70% of whatever value they're trying to predict, right? Right? And in the Blackboard, I actually uploaded example data, and this will help you in your exercise. Okay? So let's say we have a data on, so let's say we're trying to predict the number of flooded downs per daily millimeters in rainfall, right? Let's set the conventions here. The X or the independent variable would be your rainfall in millimeters, daily rainfall. And then the Y or the dependent or the variable that we're trying to predict would be the number of flooded towns. Again, rainfall data is generally easy to obtain, right? So it makes sense to make this variable your independent or your predictor variable. On the other hand, of course, flooding is sort of a consequence of your rainfall. And this could be quite hard really to forecast, right? So this would be our dependent or our response variable, or this is the value that we're trying to predict. Again, as usual, we always start with plotting the data set. Again, a simple scatter plot would be helpful. But be mindful with how you set your X and Y axis, right? So in here, our X-axis is our millimeters of rainfall. Y is the number of flooded towns, right? And right from the plot here below, we can see that, again, you more or less have a positive relationship. Again, the rainfall is increasing. The flooded towns, number of flooded towns is also increasing. So that's a positive relationship. Again, you can see more or less that the values are more or less lining up on a straight line. So it's a linear one. And you can also see that the data is actually more or less, there's a minimal gap in your data set. So you can see that it's probably a strong relationship. Outliers, maybe this one, but again, maybe not. Okay. So again, this is quite an subjective one, but maybe there's no outlier really. I mean, subjectively speaking, okay? Because in here you can see that, so I fitted a trend line on the data and I tried to obtain the regression equation for this one, and also trying to obtain the coefficient of determination, and you're seeing a coefficient of determination of 0.95, right? Like it means that the phenomenon of flooding in the towns, right? The variation and the number of the flooded towns is actually explained, or 95% in the variation of the flooded towns is explained by the increase in your rainfall. So I think from that metric, I can say that there's no significant outlier in this data set. Right, I'm just gonna quickly show you how we did how I did this plot. So I'm sure you're quite familiar with this one, but just for the sake of having a refresher, right? This is the data set. I'm gonna hide the chart. So just insert a chart. Okay, so you can also do this in R. But for now, since our lesson is about Excel, which Excel is always readily available when you start working, it's probably the most easily accessible software for statistics. So we're doing it in Excel. Yeah, so just insert a scatter plot, a blank one, and then just select your data, add, and then first you have to select your X values. So again, our X values are is consist of our rainfall data. Okay. And then the y values, these are the values that we're trying to predict. Okay, so I selected the number of flooded towns. Again, you get this plot. So you can also add chart elements. So of course you know this already. Okay, I know that, but I forgot about this one. Okay, so I had to relearn everything. So more or less, this is how you can, or how you can visualize, right, a data set. Okay. So from there, you can observe the patterns like the direction of the relationship, the linearity, the strength, and then the presence of outliers, which is quite subjective, to be honest. And again, in Excel, you can also add the trend line, right? And you can sort of play with different shapes, but for now, we're going to stick with linear. And you can also add your R squared or your coefficient of determination and your equation, right? Right? So it's quite simple. um, we're not really done yet, right? So this is just one way of doing a linear regression. You can just do it using a scatter plot. That would be probably the fastest way to do it, and it's quite foolproof because you can see the data right away. Okay. But we also have another one. We also have the line estimate or the line nest formula in Excel, right? You simply have to type the linest function and then just input the y values and then your x values. And the result would be you will get the b or the slope and then the y-intercept or the a. And this is very useful again for when you're trying to do a simple analysis and you need to get the slope and y-intercept quickly. Okay. So I'm gonna show how this was done. So just select an empty cell, type your linest formula, and then just select your known y value. So again, it's our flooded number of flooded towns. And then you can either hit comma or just hold control. And it will automatically output into two cells, right? So the first one is the slope of the regression. It's 0.432. And it's just the same as the slope that we got from the scatter plot trend line. And then the y-intercept is -16, which again, it's just the same as the one we got from the scatter plot, right? How do we interpret these values? Again, the y-intercept is more or less -17. And again, there's no way you can get a -17 number of towns. So we can also interpret this the other way. So it can tell us that the number of flooded towns will hit a non-zero value upon reaching 17 or 16.96 divided by the slope. So 16.96 divided by 4.43, you'll get something like 39.24 mm of rain, right? So once you hit 39.24 millimeters of rain and you get values exceeding that, you will start seeing towns get flooded. Okay. Now, since we're doing statistics, again, we have to account for the error. Okay. This is easily taken for granted when you're doing maybe some when you're doing some you're playing with some equations in your geology class, but once you start working or once you start doing some serious research where your actions will have heavy consequences, okay, you may want to actually strongly consider the errors when you're doing or when you're using some regression equations. Okay. And let's go to that part. Right? The line S formula has more advanced functions. You can utilize that function of the line nest by simply select by initially just selecting a two column by five row cells. So you just have to select this size of cells, and then you have to type the line nest formula, and then input the y values and then the x values, and then set a true flag for the calculation of y-intercept so that it would normally calculate the y-intercept, and then set another true flag for the output of regression parameters, and then from there you can hit enter, and you will get a set of values, right? So I hope you can see this. The first value is the slope of your regression line. So again, this is just the same as the slope which we got from our scatter plot and our Linus equation in its basic form. We also have the same y-intercept value. And then we have another parameter here. This is the slope standard error. It's just a error. This is the error value of the slope. I'm gonna expound that later on. You also have an error for the y-intercept. Okay. And then you also have your r squared. Okay. And then error for the y estimate. This is probably the most important one. I'm gonna discuss this later on. And then you also have your f statistic. So again, I think this is also an important variable parameter. And then the degrees of freedom, and then regression sum of squares and residual sum of squares. These are just the the values which were used in deriving the regression line. I'm not gonna discuss that in detail. Right? I'm just gonna show you how these sets of values are obtained. Again, you just need to select cells, two columns wide and five rows tall. So two columns, then one and two, three, four, five rows. and then type the Linus formula, and then enter the known y's. Sorry, enter the known y's, enter the known x, and then set a true flag for the calculation of your slope. Sorry, and then another true flag for the return or the output of addition and regression statistics. Then just hit enter and you will get the regression stats values. Right, let's just define these outputs. So again, you're already familiar with the slope and the y-intercept. Not gonna expound that any further. Now let's just have an example. What is the number of flooded towns when the rainfall is 100 millimeters? Right? The first step you have to do is you have to formulate the regression equation. So again, this is simply y is equal to bx plus a. B is the slope, right? So it's 0.43 from the regression stats. X is 100 millimeters. That is our independent variable. And then A is your negative 16.96. So again, that's from our regression stats. And the result is 26.28 approximately. Okay, so we have 26.28 flooded towns whenever you have a rainfall of 100 millimeters. Right? At this point, this is just a mean value, right? So this is just a mean value of our regression model. And again, I have discussed that this is subject to errors and fluctuations in value. And if we're going to incorporate the errors, this value will definitely change, okay? Or we will be getting something else. So we're going to discuss that later on. But for now, this is the mean value of our estimate. Slope standard error, this simply expresses the error in the regression slope, and it is expressed in terms of a tilt, right? So again, when you're making regression lines, and if you're trying to account for the scatter in the data, right? So if you're trying to draw an imaginary regression line that would actually perfectly fit the area of your date of the scatter of the data, okay, you can sort of draw or you can sort of tilt your regression line, okay, and whatever tilt, okay, that how much tilt you need to perfectly fit your data, right? That would be your slope standard error. And this is actually more easier to comprehend if you convert it into percentage. So you can just divide your slope standard error by your slope. Okay, so you can get a percent error. So again, the slope standard error is 0.03 divided by the slope 0.43. You will get something like 8% error, right? So this is a bit more easier to grasp, right? But yeah, that's all. Y-intercept of the standard error. So again, it's just nice to know, right? So this is just again the error of the y-intercept. Okay. So you can also express it in terms of percent error. So you're gonna get something like 6.4%. Now this is again, as I've mentioned earlier, this is the most important for me. I think this is the most important output in your linear regression statistics. This is the y estimate standard error, or basically the error whenever you're trying to predict a y value. in your regression analysis. It's it's a this is a direct expression of the overall error whenever you're getting a y value, right? And the units of the error is just the same as the units of your response variable, right? In our example, the units of the error here is just the number of flooded towns. And we can use this to incorporate the error in our estimate. And the most common confidence interval used when you're trying to when you're incorporating our errors is the 95% confidence interval. Again, this simply means that at this at this level, right, we are more or less correct 95% of the time. Okay. Right? So how do we calculate the confidence interval or the range of values, okay, that would occur 95% of the time, right? So 95% confidence interval is equal to your y value plus minus 1.96 multiplied by the y estimate standard error. Right? Again, let's continue our example earlier. So let's say at 100 millimeters of rain, again, we know that we're gonna get something like 26.28 flooded towns on the average. Okay, but again, if we're gonna factor in the errors, this value will not always be true. So if you want to be correct 95% of the time, okay, you can give instead a range of values, okay, and just let the decision makers make sense of that value. So how do we do this? Just again, we have the equation here. So just plug in the y value. So this is our estimated, or this is the our y value which we derived from the regression 26.27.278 plus minus 96 multiplied by the standard error of the y estimate. That's 3.021. Okay, so again, this is just from the Excel stats that we have obtained earlier, and it will get you something like 26.28 plus minus 5.9. So to get the lower bound, you simply subtract 5.9 from 26.28, and you will get something like 20.35. So this is your lower bound value. So this is your low estimate. So we can expect uh, values to be yeah, so this is gonna be the lower bound. So the values will probably not be lower than this value. And then to get the upper bound, you simply add your 5.9 to your y values, and that's gonna be something like 32.199. Okay. And this is gonna be the upper bound of our values. Okay. So practically speaking, how can you use this value? So for example, if your boss wants a safe value, like you want to use a worst case scenario, that would be correct 95% of the time. So we can say that I think we're gonna get 32.2, or you can simply round that up to a whole number, right? So you can just say we're gonna get approximately 33 flooded towns, right? If we have 100 millimeters of rain. Okay. So we're gonna get at most, right, 33 flooded towns. Okay. Or if your boss just wants the minimum value, you can say, yeah, the minimum value is probably around 20 flooded towns whenever you have 100 millimeters of rain. So this is again a context specific how you're gonna use the CI. This is gonna be real context specific. Okay. Yeah, but knowing, right? Knowing that this interval of values like covers 95% of all the possible values. Okay. This could be quite powerful. Yeah. Coefficient of determination, again, in the example, we're getting like 95% R squared. So this is really a high value, relatively speaking. So more or less okay, so this is actually a good value, subjectively speaking. Normally, if you want to use this value, you would want to compare it with other studies related to flooding and rainfall. Okay. So from here, you can see how well your model is performing compared to other flood and rainfall regression models. Okay. So if your R squared is 95%, I mean that's a really good value. You have like the bragging rights. You can easily have your bragging rights, like academically speaking. Uh, the last one, this is actually also important. The F statistic of your regression. This is a sort of an indicator value that's based on the variability between your model values versus the overall variability of your actual Y values. Okay. Uh, the F statistic answers one important question. The question is whether your regression is actually legitimate or not in terms of statistics. Okay. So again, the R squared simply tells you whether your response variable is actually effective in predicting the variations in your sorry. The R squared simply tells you if your predictor value is performing well. The F statistic is answering the question on whether the overall regression is illegitimate or not. Right? So how let's expound that a bit. In regression, the default null hypothesis. So again, when we're doing regression, we're actually doing some hypothesis testing in the background. The default null hypothesis in regression, or the H naught, is that there is no statistical similarity between the model Y values, like the regression Y values, and the actual Y values. Okay. So the null hypothesis simply states that our model is not the same as our Y or measured Y values. Okay, so null hypothesis is generally a lazy statement. So it's telling you that we're not seeing anything. So it's like a sort of a devil's advocate. So you're not seeing something, you simply got lucky with your R squared. Okay. Your your 95% R squared is just due to luck. Okay. And then the alternative hypothesis, or the hypothesis that we're trying to we're trying to push, or the H1, is that there is a statistical similarity between the modeled Y values and the actual Y values. So this simply means that, wow, we actually are seeing something, or we are discovering something here, right? If the F statistic of regression is greater than the F critical, we can now reject the null hypothesis and accept the alternative hypothesis. Right? So what is the F critical? So this is another parameter that I'm gonna briefly discuss. The F critical is used as Sorry for the grammar. It's used as threshold value for the F statistic. Okay, sorry, I crammed this lecture this afternoon. So it's a threshold value which depends on the confidence level, the selected confidence level. So again, you can either choose 90, 95, 99. Most of the time, 95 is like the commonly used one, but of course you can consult whatever industry you're working on. Okay. So yeah, just check the standard confidence level that's used in your industry. The F critical is also dependent on the degrees of freedom. Right, for our example, the numerator for the degrees of freedom in our rainfall flooding example is 1 because when you're doing a simple linear regression, we only have one response variable. Therefore, the numerator for the degrees of freedom is just 1. On the other hand, for the denominator for degrees of freedom, this is simply obtained by subtracting 2 from the number of data points you have. So we have like 9 data points, just subtract 2, you're gonna get 7. So if you want to do a test at 95% confidence level, uh, the significance level or the resulting alpha level would be something like 100 minus 95%, and you're gonna get 0.05. And then again, in Excel, we can calculate the F critical using the F dot inverse dot RT function. So just input the alpha level, the numerator for the degrees of freedom, and then the denominator for the degrees of freedom. So that's something like F dot R dot IND dot RT 0.0517, and your F critical would be 5.59.144. Now we can compare that value with the F statistic, right? Our F statistic from our regression results is 1.45.70. And this is greater than our F critical. And therefore, we can now reject the null hypothesis and accept the alternative hypothesis. Now, therefore, the regression model between the rainfall and the number of flooded towns is, sorry, is statistically significant. Okay, so it means we freaking discovered something new. Okay, and yeah, so that's how F statistic works. Okay, so it simply works as a sort of a tool for for proving the legitimacy of your overall regression results. Okay, so you're just proving that your regression is not due to pure chance. Okay, so you're actually seeing or you're seeing some phenomenon and you're able to capture that phenomenon. In this case, flooding, you're able to capture the flooding phenomenon with your rainfall data. Right? Do you have questions or clarifications? I'm just gonna run through the exercise very quickly. So I think I already gave you a decent introduction into the exercise. So for now, you can simply you can just ignore. You can now just ignore the whole tutorial part in this exercise. Okay, so I think the lecture I gave you this evening, I think it's more clear compared to the tutorial in the first in this exercise. So you can just skip this part and just jump into problem 1. Okay. So this is quite straightforward. Just need to read the instructions I think this is the answer key. Anyway, okay. So just follow the questions in the exercise, right? And you can yeah, you can just simply answer them. Just I also uploaded this tutorial data. Okay. So you can see how the values were calculated, and you can also see right away, okay, how you can format your answers in the exercise. Okay. Right? Do you have questions or clarifications at this point? Okay. So far none. Okay, thank you, Ivan. Okay, thank you, Rad. Right, should you have pinagkaiba ng commented exercise file? Yung commented na exercise file,